All right, so if there are no questions, let's go on to surface area then. So this is, again, another fairly short section just because it's basically just uh, adding on to what we just did. So let me quickly show you kind of, again, what the overall goal is on this. You'll see that it is pretty similar to what we were just doing, even though it doesn't really seem that way. It seems like what we're doing here is a little bit different, but anyway, this is a picture of the situation. This is surface area is what we're talking about. So here what we have is maybe a function that, again, is defined on some interval. Okay, so that's our interval from A to B. Now the idea here is that instead of measuring the length of the arc, what we're going to do is picture just this line here, or this curve, and imagine what would happen if that curve, again, just the curve itself. Remember what we were doing before was like we would consider the entire area under the curve, right? And then we were going to revolve that whole thing around the x-axis. Remember that for the volumes of this surfaces of revolution like that? Well, instead of doing that, instead of thinking about the entire area under the curve being revolved around the x-axis, what are we going to do now? Now we're just going to talk about the curve itself being revolved around the x-axis. Okay, just the surface of the curve, that's it. So this line itself is going to be kind of revolved around the x-axis, both ends. You kind of see what's going on, and then that's going to produce like maybe some kind of a mirror image here down on the bottom there. And it's a surface now. You see, it's not a volume, it's just a surface area is what this is. So you can kind of picture like a bunch of these coming around, and then it goes all the way around into the board as well. So you're going to get this sort of three-dimensional surface. Everybody kind of see what's going on with that? So rather than getting a volume, like this would be something where you could stick your hand in there, right? And everybody kind of see what's going on with that? So it's a three-dimensional. It's actually really not really three-dimensional. It's sort of 2.5-dimensional, really, because it's a two-dimensional object existing in 3 space because it doesn't really have any volume associated with it. All right, so that's the idea. And so what our goal here then is to figure out what is that, what is the surface area of that object that we get after we revolve just that curve around the x-axis. So that's what we're up against. All right, so how do we do this? Well, very similar to what we did before. In fact, I'm just going to pick a couple of these points here. Again, let's say we pick, I don't know, let's pick the line segment that goes from here to here. So the idea is, again, that we sort of divide this up into some number of subintervals, and then we have to kind of think like, what's going to happen if we just imagine like a straight line segment like this being revolved around. So what I'm going to do again is kind of just look at one line segment by itself and just see what's going to happen to that. So if you picture just the line segment itself being revolved around a particular axis, so let's say that line segment's going to revolve around this axis here, the x-axis, okay? What is that just by itself? A line segment revolved around the axis. What kind of surface is that going to make? And the thing I kind of think of about that, those dog collars for when dogs get biting themselves and you don't want them to. That's kind of what I picture that this is. It's like one of those dog medical devices. Okay. Well, what is that object mathematically called? Yeah, a cone of shame, right? They call it the cone of shame for dogs. So, but basically what you kind of have to picture there is that if we do this, dividing the function up into a bunch of these little things, what we're going to get is a bunch of those little cone-shaped things that sort of mimic the or approximate the total surface area of the object. Object itself is going to have nice smooth sides, right? But when we approximate it with these little line segments, we're going to get these little straight edged things, a whole bunch of these little cone things put next to each other, and that would approximate the object whose surface area we're trying to find. Okay. What is this called? Do you guys know what this is called? It's kind of like a truncated cone, really, is what it is. It's like a cone with the top chopped off of it. You guys know what that's called? It's got a special word. Yeah, don't feel bad if you don't know what it is. It's called a frustum. A strange name for an object, but that's what it is. It's a frustum. And so, since it has straight sides, even though one, it's the whole overall shape of this thing is circular, we can still, there is a formula for the area of a surface area of a frustum. Okay, so that's what we're going to try to find here. Surface area of a frustum. So what a frustum has is a length that I've just labeled there as L, and it also got two different radii associated. It's got an R1 radius, and then it's got an R2 radius. You see that? So there's a 1 radius on the small end, bigger radius on the big end. That's just what we need to identify what the surface area of a frustum actually is. Now, rather than going through the whole spiel about deriving the formula for this, I'm just going to tell you what it is. Surface area of a frustum is pi r L. Yeah, 2 pi r L. 2 pi. I'm using a small r because that's what the book does. So 2 pi r L. But again, yes, this is the surface area of a frustum. And then, why would we be interested in the surface area of a frustum? Because what we're doing is we're approximating the total area of this surface of revolution with a bunch of different frustums sort of stacked together. That's the idea here. So that's what we kind of have to picture. A bunch of frustums added together. So if we could figure out the area of one of them, well, then we could figure out the area of all of them and just add them all up. And then that would be an approximation to the exact area. And then you get where we're going with that. Approximation, we take the delta x, let it go to 0. That gives us the exact surface area. Now, one thing just to notice here, in that formula, there's just an r. There's not an r1 or an r2. So we have to define what that r actually is. That r actually turns out just to be the average of the two different radii that are in the frustum itself. Okay, so r would actually be the average of the two, which is kind of like the one right in the middle here. That would be the r, okay? So whatever the average of those two other radii is, that's the r, okay? All right, so, and if you can, you might even be able to see that this is actually very similar to the area of a cylinder, because that, if this was just a straight cylinder, then that r would just be the radius of the cylinder itself. So 2 pi r is the circumference of it, right? That gives us like the one dimension, and then the multiplying it by L gives us that second dimension on it. So anyway, that's it. So this gives us a way to figure out what the total area of a frustum is then. And really what we're doing here, it turns out that, when we actually decide what we're going to be plugging in here, remember that when we divide these up, we pick a point that's going to be sort of in the middle of, or somewhere between the two endpoints of any particular subinterval. So we would call that like x1 star, and that's the value that we would plug in like right in the middle of each approximating rectangle. And so that would be like x2 star in the middle here. So anyway, all it is, it's just a point that happens to lie on each subinterval. And it turns out that if you pick the point that's right in the middle, that in fact is the average. That's the r value right there. It's like right between the two endpoints there. Okay, so it turns out that that is itself a y value. If you can see that when you plug that r in, see, when you plug this, you plug in a particular x value, like the x value would be right here, right? So that's like your x sub I star. And then that plugging that into the function gives you a height. So really that height ends up being the f of x sub I star. Or if you want to just call it y sub I star, you can do that. So that's what that height is there. Okay, so when we want to figure out what the exact surface area is, what do we get? I'm going to skip the summation stuff because it's really similar to what we just did. You have the 2 pi on there. That just comes from the formula for the area of a frustum. Integral from a to b. And then you have that r there, right? The r, we just said again, was this. R is just the height that the function, when you plug in that x value, you have to go to some y height there. So I'm just going to call this f of x. And then the L, what's the L, right? What is this L right here? Well, that L, this is why I said this is kind of similar to what we had just done. What is that L? Well, the L is just simply the length of that bit of arc right there, right? Well, remember, we already found that, right? The length of that bit, and again, translating it into an integral, that's just the formula that we already had for the length of some arc of a function. And so that, we already know what the formula is for that, and we just plug it in. So that's the 1 plus f prime of x squared. So really, it's kind of just using the formula that we already had, but it's got this other couple of things that we have to have here. The 2 pi for one, and then this f of x there as well. Okay. Now this is going to work if your function is defined in the y equals f of x way. So this is like if y equals f of x, and it's about the x-axis, okay, because this is what we've drawn, right? We're revolving this thing around the x-axis in that picture up there. So, but what if you were to revolve it around the y-axis instead? Let's kind of see what would happen there if we did that. So if you were going to do this around the y-axis, well, the only thing that really changes is that height of the line segment that you're looking at. So suppose, for example, I had a function that maybe did this, right? Here's my a and b. And suppose that I wanted to revolve that thing around the y-axis now, not the x-axis, okay? So if I did that, then, you know, kind of the picture would look something like this. You would have this going around. This part would go around too. Function would sort of be mirrored over here. Right, and it would continue on around. Kind of like a alien ship or something like that, huh? Except remember that you could put your hand on the inside of this thing because it's just a surface area there, right? And so thinking about what would be different here, like on the other one, when we revolved around the y-axis, we had to think about what this distance was here. We called that distance f of x. Well, here, now the distance is going to be different. Now the distance is, since it's from the y-axis, this is the distance that I would be interested in. Notice that that distance is actually x now. So if it's about the y-axis, how does this function, or how does this formula change? Well, then the area in this case is going to be 2 pi times the integral from a to b. And instead of having a y there, because remember that this is really a y, right? Y equals f of x. Instead of having a y value there, what would I put instead? Well, I just put an x there, okay? So that's the difference. Do you put a y there or do you put an x there? And if it's a y, you have to actually call it f of x. Well, you could call it f of x. So you see the difference here. In fact, if you want to just sort of summarize these here, you could even do this. But the x-axis, how is this going to be different? Well, I already wrote the formula, but you could also write that formula like this. You could write it as 2 pi integral from a to b. You could put a y there if you wanted to. And the way that you have to kind of view this is look how you are integrating, right? How are we integrating these? Well, we're integrating them with respect to x. You see that? The dx on the end there. Again, that's important that you have that dx there. That dx on the end there is telling you if this letter matches, and notice they're all x's here, you can just leave that as an x, okay? You don't have to do anything funny with it. However, if these letters don't match, this is kind of like that stuff with implicit differentiation, if you remember in Calculus 1. If these letters don't match, here's a dx on the end and here's a y here. Well, what is that? The fact that this is a y here and this is a dx here means we have to put this y in terms of x. So we would have to write it as f of x. You see what I mean? In other words, we'd have to put the entire function right there, whatever that function happens to be. Okay, so, and then if you look at the formula sheet there, you see there's actually 4 formulas there. So what's the deal? Why do we have 4 formulas? Well, all of these are if what? These are all if we have the function defined in this way. If y equals f of x, then these are the 2 formulas that we'd have. Again, notice dx is everywhere, right? So if y equals f of x, you're going to have a dx on the end of the thing. What if, on the other hand, you have the function defined x equals g of y? Well, then things change. If x equals g of y, then it's still really almost the same, except now we're going to be putting a dy on the end of this thing. And in fact, let's do, sorry, let me just do this about the x-axis. If x equals g of y, then the area is going to be 2 pi. Again, about the x-axis just means that you're going to have a y there, because the distance that you need to get from the x-axis up to whatever the function is, that distance is a y distance. So you're still going to have a y here. And then notice this is now going to be f prime of y, or dx dy squared. And then you're going to have a dy on the end here. And now notice here, if the letters are matching, again, that just means this just stays as a y. You don't have to put anything else there except just a y. That's it. On the other hand, if you're doing this around the y-axis, then things change a bit as well. And I'm going to, don't worry too much about like trying to memorize all 4 of these things and like when do you use each of them. Okay, good question. The question is, what happens if they're rotated around lines other than the x or y axis? Fortunately, in this case, we're not going to worry about that situation. All these ones will all be either around the x or the y axis, and that's it. We're not going to worry about any other axes. So that takes a little bit of a load off, I hope. Trying to decide which of these 4 formulas we're going to use. Oh, and I think they're using C and D here. It doesn't really matter, but anyway. Here, now it's the y-axis. Again, the distance from the y-axis over to whatever function you're doing, that's a horizontal distance, so that's an x that we have to put here. Okay, so we put an x there. But again, the function is defined to be g of y. Oops, and I should probably call it g of y, not f of y. We put g prime there instead of an f prime. And again, this could also be called dx dy. But notice, if this is the way the function is defined, what do we get? We get dy's on the end here. If they match, all you have to do is just put the y there. If they don't match, like in this case, instead of putting an x there, what do I have to put? Well, I actually have to enter the function itself, g of y, whatever that function happens to be. Okay, so like if g of y was x squared plus 1 or whatever, I would have to put an x squared plus 1 right there in place of that x. Okay? Now, fortunately, all of these can be really condensed into nice, simple little formulas. And so if you see at the bottom of that explanation stuff there, it says for rotation about the x-axis. And again, this doesn't even matter how you define it. As long as you realize what that ds is, and I'll talk about that in just a second here. But the surface area, as you can see at the bottom there, if it's around the x-axis, then what? Then you just put the integral 2 pi, and again, about the x-axis means horizontal axis, but the distance from that axis up to whatever function is up there, that's a vertical distance, so you have to put the y there. Right, so this is going to be a y, and then you put ds on the end. And if it's about the y-axis, then the distance from, this is a vertical axis, now the distance from that axis over to your function over here, whatever the function is, that's a horizontal distance, so you have to put an x there. So here s is going to be 2 pi x ds. Now what the heck is that ds there? Well, the ds in fact turns out to be from the previous section. Just let me quickly remind you of that. From the previous section, suppose I was, I had a line segment, right, and I was trying to approximate that line segment with a straight line, right? And I was trying to figure out what that L was. I'm just going to call it S here, though, for now. How did we do that? So again, the idea is I've got a curve and I'm approximating it with a straight line. In fact, I don't even really need to have that drawing. Really all I need to look at is just the ds itself. So I look at a little line segment, and that line segment we're going to call ds. How do I get that ds? Well, I have a small change in x. In fact, I should use a d there, not a s. In fact, I'm going to call this one delta s for now. I have a small change in x, and then I have a other small change in y, corresponding change in y there. Well, it turns out, if you could see, where is that ds actually coming from? That's coming from directly from the Pythagorean theorem. You see, what is the ds? Well, if you square it, you're going to get, the Pythagorean theorem says this would be delta s squared equals delta x squared plus delta y squared, right? So if I want to solve for ds, I would just take the square root of that. And so I would get the delta x squared plus the delta y squared. And then you can actually take the limit of this. The limit of this is going to, in limit, these become differentials. So ds itself is actually going to be dx squared plus dy squared. And then you can go through that whole process where we factored stuff out of there. Like suppose I were to factor out a dx squared, right? What if I do that? If I factor out a dx squared, then I'm going to be left with 1 plus dy dx squared, right? And then I can take that dx out of there, and you see what that's going to turn into? It's going to turn into the exact formula that we just had, right? 1 plus dy dx squared, and then that dx kind of floats out to the outside there. So this is one interpretation of what ds is actually going to be. If you follow this through, ds is, in fact, exactly this. So you can see what happens if I were to replace that ds with that. Well, what would I get? I sort of come back up here and say, well, I would get exactly one of these formulas that I was just talking about, right? Do you see that? So, but that was by factoring a dx out of there. But I could have also, instead of factoring out a dx from under there, I could have done this, right? I could have factored out a dy instead, or dy squared. And if I would have done that, then I would have gotten dx dy, and that would be squared. And then from the other one, I would have gotten a plus 1. And then that one, I could take that dy out of the radical and gotten this. I could have gotten 1 plus dx dy squared. And then the dy would have come out. And you see, again, that is also ds, right? ds could be also viewed to be that. Either of them is fine. If that's the case, then which formulas would I have gotten up here? Well, I would have gotten these two, right? The ones that have the dy's on them. If I would have done it the first way, I would have gotten the ones that have the dx's on them. So you can see it just depends on how you interpret what this ds actually is. You can interpret it either way. That if you define your function, this would be like if you define your function y equals f of x, right? Then that's the one you would use because it ends in a dx. If you define your function x equals f of y, well, then this would be the one that you would use because, again, it ends in the dy rather than the dx. Okay? So this sort of just condenses these formulas really into just two, and then you just have to interpret what ds actually is. So if you can kind of put this all together and sort it out in some kind of logical way, I guess, the first thing you would have to ask is, how is my function defined? Is my function defined y equals f of x? In other words, is it just x's in the function? And if it is, then my next question would be, okay, if it's y equals f of x, I know I'm going to have a dx on the end of that thing, right? There's going to be a dx on the end of my integral. And then I have to decide, am I revolving around the x-axis or the y-axis? If it's the x-axis, then I'm going to have to put a y in front of this, right? So that would be this case right here. It's around the x-axis, I would have to put a y there. If it's around the y-axis, I would have to put an x there. And then again, depending on whether it's y equals f of x or x equals f of y, that ds, I would choose the one that I need. If it's x equals f of y, I would choose the one that has the dy on the end. If it's y equals f of x, I would put the one that has the dx on the end. Okay. And by the way, just to let you know, if there is a surface area formula on the test, I will be providing all 4 of these formulas for you on the test. This test actually has a formula sheet. Okay, so comment more like the shell method for 2 pi if rotate along x, use the opposite. Yeah, kind of. I guess you might want to think of it as the idea of being perpendicular to the line axis of rotation or parallel to it. Yeah, maybe. But yeah, anyway, this is the idea here. Whatever axis you are revolving around, you're going to use, so like if it's a horizontal axis, the x-axis, then you have to have a y for the distance away from the function, right? If it's a vertical axis, you have to have an x there. And whether you put an x or f of y depends on how the function is actually defined. Okay, so anyway, let's do a couple of these and just decide maybe which of the 4 formulas we want to use. Okay. Any questions on this? And again, this will be provided with you for you on the test. These formulas will be, so you don't have to memorize them. All right, so any questions? If there are any, just go ahead and write them in there. Otherwise, we'll go ahead and go through a couple of these problems. So this is example 1. Find the area of the surface formed by revolving the graph of f of x equals the square root of x on the interval 0, 1 about the x-axis. This is around the x-axis. The function is defined in the normal way, y equals f of x. So we're going to use the first formula here. So basically, I need to find the derivative, f prime of x. And again, we know that's x to the 1/2 power. So f prime is 1/2 x minus 1/2, which we can write as 1/2 root x. Might as well go ahead and square it too. F prime of x squared is going to be 1/2 root x squared. That's going to be 1/4x. Okay, so the surface area here, S, is going to be equal to integral, well, I guess this one we have to put the 2 pi on the front, 2 pi integral from 0 to 1 of, now in this case, again, we're revolving around the x-axis, so we have to put a y there, right? But the y, we're not going to put a y, we're actually going to put the function, the f of x function there. So I'm going to go ahead and just put the square root of x there. That's the y that has to go there. And then the square root of 1 plus 1/4x dx. Okay, so everybody see this is the y that has to go there. But again, because of the non-matching letter, we actually have to put the function, how that function is defined in terms of x. So if this was around the y-axis, what would I put there? I would just put an x, that's it, just an x. Because the distance from the axis to the function is just simply x, that distance. Remember that if it's around, whether it's around the x or the y-axis, if the function is defined in this way, f of x, I have to have that dx there. Okay, so I'm not going to ever see a dx, or I'm not going to ever see any y's anywhere in here. That's what I want to avoid, putting any y's at all there. Okay. So if it were just around the y-axis, what would I put there? I'd just put an x. That's it. Okay. We'll do some more examples so you can hopefully see how this is working. Anyway, now the goal is to actually evaluate this integral. How do we evaluate this integral? We've got a square root of x times another square root. Well, remember what you do when you have a root times another root. What can you do? Well, remember root A times root B is the same as root AB. So the goal here would be to just put these under the same radical. Everybody see that? Since they're both under radicals anyway, you can combine them under a single radical. And so now that they're under that radical, now we can go ahead and distribute that x in there. So we'll get root x plus, if I distribute the x there, I'm just going to get a 1/4. Okay, so now to do that integral, I think the best way would be to just do a substitution. U is going to be equal to x plus 1/4. Du in this case is nice, it's just going to be dx. And so with that, the integral is going to become root u, right? Just root u, du. And the whole reason I'm even doing a substitution here is because we have those bounds, and so we want to change those two. The lower bound is now going to be 1/4, right? If I plug in 0 to that substitution, I'll get 1/4. If I plug in 1 plus 1/4, 5/4. So my top bound is now 5/4. Okay. And again, that's coming directly from, just plugging in the old bounds into the substitution. All right, so that's the same as u to the 1/2 power. So the antiderivative of u to the 1/2, we have to raise that by 1. We get 3/2. We'll have a 2/3 in front of it, 2/3 u to the 3/2 power. Plug in the 1/4, plug in the 5/4, subtract, I guess in the other order though. So that's going to be what, 4 pi over 3, let's just combine the constants. 5/4 to the 3/2 power minus 4 pi over 3 times 1/4 to the 3/2 power. So whatever that is, decimal approximation, that's the surface area of this particular function being revolved around the x-axis. All right, so again, try to just remember what you need to put in this part of the function. That's real, or in this part of the formula. That's kind of maybe one of the big sticking points here. But what are you supposed to put there? Well, just remember, whatever it is, it's got to match. Those letters have to match. Okay, so let's try the second one. Some of these actually they're pretty similar to what we just seen as far as like arc length is concerned, but some of them actually are, believe it or not, easier to find the surface area than the arc length. Sometimes the arc length is actually a lot harder to find than the surface area. So in fact, this is one of them. We'll see why. So in this case, let's just kind of review what we've got here. We've got 9 minus x squared. So this is a y equals f of x function. We're definitely going to be wanting to use that form that has the dx on the end of it, not the one that has the dy on the end. And notice this one is around the y-axis, okay? Y-axis. So the surface area here, 2 pi integral 0 to 3. So what should I put here? I have to put something here, right, before the root. What's that something going to be? A y or an x? Just an x, that's it. I'm around the y-axis. So what's the distance from the y-axis to the function? It's just x, okay? And then since I have a dx on the end of that, that's all I need. I just put an x there. I don't have to put a f of x or anything like that. And then 1 plus, actually, let's go ahead and find that derivative here. F prime here, this is pretty easy. It's negative 2x, right? And then f prime squared is going to be 4x squared. So that's what's going to go here. 1 plus 4x squared. And then the dx on the end. Okay, now here's another question. What if I were revolving this around the x-axis? What would go in this spot right here? What would I put right there if I were revolving around the x-axis? Right, exactly. I'd have to put the y there, but again, I can't have these letters not matching. So instead of putting a y, I would actually have to put what y actually is. Well, y is equal to 9 minus x squared, so that's what would have to go there, okay? Now you can kind of see what I mean by this when I said that sometimes it's easier to find the surface area than it is to find the arc length. If I were doing just the arc length, well, that wouldn't even be there at all, right? And I would just be having that for my integral, the square root of 1 plus 4x squared. Well, that integral is a hard one. What method do you have to do if that x were not there? Just the square root of 1 plus 4x squared by itself, integral. Well, that one, that's right, that's a trig sub, and that's actually a very difficult trig sub. That would be one that would end up with a secant cubed inside of it. It would be a difficult integral. With the x here, though, since we're doing a surface area rather than a arc length, that x is there now, right? And since that x is there, when we've got that in there, this is just a really easy regular substitution. It's not a trig sub at all. It's just a nice easy u equals 1 plus 4x squared. And so then du is just 8x dx. And there is the x dx, right? That's why having that x there is nice, because now we can take care of that du, or the du takes care of it. Okay, and so then we'll just divide both sides of this by 8. So again, then you see this x dx together, those two together become the 1/8 du. And so our new integral here in terms of u is going to be 2 pi, and we'll take that 1/8 out front, and then we'll have just root u here, and then du. And the lower bound would end up being 1, and the upper bound would be, what is that going to be? 37, I guess. Right, plug in the 3 there. 3 squared is 9, times 4 is 36, plus 1 is 37. So there's our new integral in terms of u. And so this becomes pi over 4 antiderivative of u. Yeah, so just plugging in the 37 and the 1 is all I'm doing there to get to this answer here. Just doing the fundamental theorem there, plugging in the two bounds, subtracting. All right, so let's work on these problems that are on the worksheet, problems 1, 2, and 3. Yeah, these are, I think, all good ones because it kind of forces you to think about, is my function y equals f of x? Is it x equals f of y? What do I need to put there right before the square root part? And that third one is actually pretty good because that one you can actually choose to solve for x or y, and you maybe want to think about like which one is the best given that you're revolving it around the y-axis. Okay, so that first one, let's see, we're revolving it around the x-axis, and it's a normal y equals function. So the distance from the x-axis to the function would have to be considered to be y. And so you notice in the formula, that's where the y is, right? Right there. So he puts the whole function there, right? And then leading up to that, this is just chain rule derivative, right? We have to put the 1/2 out in front, lower the power by 1, and then why is this e to the x right here? That's because of the chain rule. Derivative of 1 plus e to the x, and all of this stuff here is e to the x, and so that's why we have that outside. Simplifying the derivative, you get that. Squaring it, so that's squaring the derivative, gets you all this, and then simplifying it to that. Adding 1 to it, so you see how he's written the 1. This is the 1. Why would we want to do that? Well, because we want to add them together, and so we need a common denominator. So if you write 1 as 4 plus 4 e to the x over itself, that's just 1. It now has the same denominator as this one, right? And so that allows us to combine the numerators over that common denominator. And as I've mentioned before, that idea of recognizing this perfect square trinomial, it's important to be able to do that. that's in fact what's in the numerator there is in fact a perfect square trinomial. And that's how it factors to be this e to the x plus 2. So definitely try to get used to recognizing those perfect square trinomials and seeing that it can factor in that way, especially in these two sections. That kind of thing is probably going to happen, you know, it's fairly common. Okay, and then you take the square root of it. Well, now that we recognize that this is a perfect square trinomial, this whole thing is now all a perfect square, right? Everything in there is a perfect square, except for the denominator, right? The denominator isn't. So when you take the square root of it, you see it all becomes that, except that denominator, right? It was 1 plus e to the x. You have to take the square root of it. That's why this 1/2 power is on it. Okay, but they're clever in the way they did this problem, because if you see, when you actually do multiply it by that y that we were talking about before, right? This thing here, look, it's the same as that thing that was in the denominator, taking that root, right? And so what happens to those terms? They just cancel each other out. So this is it's basically the authors of the book being a bit clever here about trying to get these things to form an integral that's doable. And really all that's left when you do that, notice the 2's cancel here also, right? The 2 pi, there's a 2 right there, and there's a 2 right there that came from the square root. Those do cancel. That's why there's no more 2 pi right there. You see there's the pi there now, because those 2's canceled. And then everything else canceled, and all we had left was just that. So that's nice. After all of that canceling and rearranging and square rooting and all that stuff, we just ended up with this nice integral. And then the antiderivative of that is just e to the x is just itself, its own antiderivative, and then antiderivative of x is, or of 2 is just 2x. Then you just plug in the 1, then you plug in the 0. After all that, numerical answer, pi times e plus 1. On the second one, again, in that one, notice it says we're revolving around the x-axis, and it says that this is a x equals g of y type function, right? And so when you see that x equals g of y type function, sort of jumping down to here, you notice you have to have the dy on the end of this thing, right? That means everything else needs to be written in terms of y. And since it's around the x-axis, what's the distance from the x-axis up to a function, regardless of how it's defined? It's just y, right? The distance from the x-axis to the function is y. Since all of these are already written in terms of y, all we have to put right there is just the y. You see, we don't have to change it into the function there, okay? So I hope that's clear about what's going on there. And then the rest of what he's doing here is just taking the derivative, and again, in this case, it's called dx dy. Take the derivative. That's another chain rule right there with the 2y, derivative of the y squared on the inside, the chain rule. Simplifying the derivative, you get this. Squaring it, you get this quantity here. Simplifying it, you get this. It looks pretty nice. Adding 1 to it, and again, once you add 1 to it, you see what happens, right? You get this. And what is that? That's a perfect square trinomial, just as we've been seeing in a lot of these problems, right? It factors to be that quantity squared. And since that is the 1 plus dx dy squared, and then you take the square root of it, that root takes away the second power, and that's what you get. Okay, and so then when you multiply that by the y, like we were just saying earlier, you only need to put a y there. You get this nice integral here at the end of that antiderivative. All the rest of that stuff's just some arithmetic, and at the end of all that, you should get that. And then finally on that last one, just again, before you even start it, you can look at this function here and realize that it's implicitly defined, right? This is an implicitly defined function. So you could, in fact, use implicit differentiation here if you wanted to, you know, decide whether you want to have dx dy or do you want to have dy dx. Well, if you think about it, like what is the best option here? It says it's being revolved around the y-axis, right? So that's a vertical axis The distance from that vertical axis over to the function, that's a horizontal distance. That's an x that you're going to have to put there. So would you rather see an x here, just an x, or would you rather replace that x with the function? Well, I think, generally speaking, it's probably best to just have the x there, not have the whole function of x there. You see what I mean? And if that's the case, if you just want to have an x there, well, then that probably means you want to have a dx on the end of your integral. Okay? How do you have a dx on the end of the integral? You solve the original function for y equals something something, right? So that's why he chose to put the y equals rather than trying to solve this for x equals and putting it in the form g equals f of y. You see kind of what I'm talking about there? You have a choice, like I say. You can solve it for x or you can solve it for y. Why did we want to solve it for y in this case? Again, because of the way that the function is saying we want to put this around the y-axis, so we want to have an x there, not a function of x there. So that's why we did that. Okay, but once you do solve it for y in terms of x, then you have to take the derivative. Again, this is more chain rule stuff going on here. That's the chain rule because of this derivative right here, inner function, right? It's the negative x to the 2/3. Got to have that tacked on there because of the chain rule. Simplifying the derivative, you get this thing here. Squaring the derivative, you see what he did. All of those, that was a 1/2 power, so basically that just gets rid of the 1/2 power. It also gets rid of the negative sign. Denominator, you're squaring a 1/3 power, it becomes a 2/3 power, right? And then again, like that 1/2 squaring, that just makes it go away. Add 1 to it, and again, you can see how he wrote 1. He wrote 1 as x to the 2/3 over x to the 2/3. Why? Well, because you want to have a common denominator, right? That's the denominator for the other term, so you want to have an x to the 2/3 in the denominator. And you see that that works out pretty well because look, you've got x to the 2/3 in the numerator. Well, from that other one, we had the minus x to the 2/3, right? So those just canceled each other out. And so all you have left in the numerator is just a 1. That's it. And then you can write this as a negative exponent. And then, again, multiply this by the x right here, right? Because of the fact that it's being revolved around the y-axis. That changes this to a 2/3 power, but still, it's a nice, easy integral to do. Raise it by 1, divide by the thing you raise it to, you get that for the antiderivative. Plug in the 1, plug in the 0, get a nice final answer there.